So here's an example where we've got some solid potassium and some water to give us hydrogen gas and potassium hydroxide, which has been dissolved in water. And you can see this is a exothermic reaction. It's giving off heat. We can see some flame being produced as well. And you can see in this case, it's a balanced reaction. Are we balanced? No, we're not. This is not a balanced reaction. I was almost tricked, wasn't I? Look at our hydrogen. Okay, so we're not balanced in hydrogen. So to balance this equation, what will we do? Let's have a think about this one. We can put our coefficients in. Okay, so we've got 3 hydrogen on the right hand side. What we might do is, to make that even, we'll put a 2 in front of our KOH. Now we've got 4 hydrogen on the right hand side, and on the left hand side we can make 4 hydrogen by putting a 2 in front of our H2O, and of course we're going to need a 2 in front of our solid potassium as well. And now we're balanced, aren't we? So we'll have 2 potassiums, 4 hydrogen, and 2 oxygens and 2 oxygens. Okay, moving on. Here's another exercise. When blue light shines on a mixture of hydrogen and chlorine gas, the elements react explosively to form gaseous hydrochloric acid. What is the unbalanced equation for this process? A, B, C, or D? Let's have a think about this. So we've got a mixture of hydrogen and chlorine gas. They must be our reactants. Hydrogen and chlorine gas. Okay, so I can only really see 2 options here that make sense, which is C or D. So which will it be? Hydrogen and chlorine gas. Well, if it were C, okay, and we had hydrogen and chlorine on their own, these don't usually exist in a stable form, do they? So typically we would see these being charged, so we'd probably have a H plus and a Cl minus. So it's not very likely to be C. It's going to have to be D, because hydrogen and chlorine gas, when they're in their gas form, they're going to exist as H2 and Cl2. And this is something to be aware of. So in future, if you see a question where hydrogen gas is mentioned, you know that it's going to exist as H2 and not just a hydrogen atom on its own, because that's not going to be stable. Let's have a look at the types of reactions that occur in aqueous solutions. So these are water-containing solutions, okay? Reactions of inorganic compounds can be classified into 4 main types. We've got precipitation reactions, redox reactions, which we're going to have a look at later on, complexation, acid-base reactions. Okay, these are our 4 main types that we're going to observe in aqueous solutions. And they've got different properties. So precipitation reaction, this is the electrostatic attraction of cations and anions to form an ionic lattice. And what we're seeing with precipitation reactions is that we're forming a solid in an aqueous solution. So we're starting with some solution or 2 solutions that we're going to combine together, and we're going to see a solid forming. In a redox reaction, we've got the transfer of 1 or more electrons from reducing agent to oxidizing agent, and then you've got a subsequent molecular transformation after the electron transfer. We'll have a look at these in more detail later on. So redox reactions are so important and so special in chemistry, and also you'll need them as well in biochemistry and biology as well, because electron transfer is one of the fundamental aspects of how living systems actually produce energy from the foods that they metabolize and from the air that they breathe and so on. Okay, so the electron transfer process is something that's going to be important later on. This is important to have a look at, and this is actually going to be covered later on in this course. Complexation is the formation of covalent bonds between a transition metal species and some ligands. And as you can imagine, those transition metal species often change their charge as they're doing this. Okay, and we get these actually produce some very nice color change reactions. And you've got acid-base reactions where you've got the transfer of a proton. Now remember, a proton is a hydrogen ion from the acid to the base. And we're going to be working with these later on as well. So, let's have a look at the concept of atomic mass. So atomic mass is the mass of a specific isotope of a particular atom. Okay, and quite often we use, you've probably seen on the periodic table, we use atomic weight, which is the average atomic mass of the naturally occurring isotopes. Now remember, an isotope has the same number of protons but a different number of neutrons, and we're going to get an average weight, and these are the atomic weights that we use in chemical calculations. You can see here, for example, that nitrogen has an atomic weight or a relative atomic mass of 14.007. Okay, and this is an average of the masses of the naturally occurring isotopes. Molecular weight. So molecular weight is also known as formula weight or molar mass. It's the relative mass of an entire molecule. Okay? Now, this is calculated by adding the atomic weights of all of the atoms in the molecule together. So this is given in atomic mass units, and the unit for this is grams per mole. We'll cover what a mole is very soon. These are measured in terms of grams per mole. Okay, so for example, lithium oxide can be calculated as 2 times 6.941, lithium having a weight of 6.941, plus oxygen, which is 15.999, to give us 29.881 atomic mass units. Also, we could say 29.881 grams per mole. So let's calculate the atomic weight of potassium chloride. So potassium is going to have an atomic mass of 39.10 plus our chlorine, which is 35.45, gives us 74.55 grams per mole. And for sodium carbonate, 2 sodiums, 1 carbonate, so 2 times 22.99 plus 12.01 for carbon plus 16 times 3 for our 3 oxygens gives us 105.99 grams per mole for our sodium carbonate. Okay, chemistry is like cooking in a way. So we've got some reactants, and these reactants are combined and they react in a chemical reaction to give us a product. And the product or products are different from the reactants that we've put in, but we haven't created or destroyed any matter. So for example, if you're making a cake, it might be something like 3 eggs, 2 cups of flour, 1 cup of sugar, some butter, a cup of chocolate. Put all of that together, you get 1 cake. So what's happening here, and don't get confused by this later on, is that we're taking all of these different things. So how many objects do we have in total on the left-hand side? So we've got 3 eggs, we've got 2 cups of flour, we've got 1 cup of sugar, we've got 1 cup of chocolate. So we've got 5, 6, 7, we've got maybe 8 different things, maybe more, that we're combining together to produce only 1 thing on the right-hand side. So only 1 object on the right-hand side, okay? And this can be very confusing in chemistry, where you're wondering, okay, why are we combining so many different things to only make 1 or 2 things on the right-hand side? Well, it's just a bit like cooking, where you might be making a cake out of all of these different ingredients. So the laws of conservation still applies in definite proportion. Okay. We use the term mole. Why do we use the term mole? Well, let me refer to the orange feather example. Okay? the orange feather example.